Before we start, I would like to briefly introduce Furqan. And Furqan is a research fellow now at Institute of Cancer and Genomic Science within our university, and he has obtained his PhD from computer science from University of York. And his primary research includes exploring edge-based operators for graph identification. His current research topics including developing and applying novel graph-based algorithm and network-based approach for biomedical and clinical setups. Yeah. And without any further ado, Furqan, let's begin.
Okay, thank you, Jimmy. So thanks for giving me this opportunity to present my work today. I am going to talk about backtrackless walks on a graph and how they can be used to characterize the structure of a graph and some of its applications and then its connections to the edge-based Laplacian. So most of the work that I'm going to present today is part of my PhD thesis, which was supervised by Professor Edwin Hancock and Professor Richard Wilson at University of York. So, well, what's a graph? It's consists of a set of vertices and set of edges. Graph can be directed, it can be weighted, and it can be labeled. In case of weighted or labeled graphs, you're given a function that assigns a weight or a label to every edge or vertex of the graph. Why graphs are important? Because they are considered as one of the most generic data structures. And that's why they are widely used in different scientific disciplines. Sometimes the term network is also used to describe the same data, but historically the term graph is used in more machine learning communities and refers to an abstract data structure, while the network usually describes a graph with the which is obtained by modeling some real world problems such as social networks, etc. So before going to the main results, some definitions. A random walk of length k is a sequence of vertices such that the consecutive vertices in the sequence are connected. A backtrackless walk is a random walk which does not allow backward steps, or it's also called tottering. A cycle is a walk whose first and last edge of the vertices is also connected. The R multiple of a cycle is the cycle which is formed by going through R times around the cycle C. We say that a cycle has tail if C square has backtracking, and a prime cycle is a one that has no backtracking and no tails. So it's important to understand the difference between characterization and representation. So for any object, by characterization, we mean that finding a list of features that can somehow use to represent that object in a different space. Representation is a special case where we can reconstruct the object itself from its properties. For graph, there are many ways to represent a graph, but two widely used representations are the adjacency matrix and the Laplacian matrix, which has some interesting properties as well. So the adjacency matrix, they both are actually matrices of size v by v, where v is the number of vertices in the graph. So the kth power of the adjacency matrix represents the number of walks of length k. The Laplacian matrix is the discrete analog of the continuous Laplacian in analysis. So this Laplacian can be used to simulate partial differential equations such as heat equation or wave equation on the vertices of the graph. Right. And it has found applications. For example, it can be used for dimensionality reduction and from other applications as well. Now the problem with the graph representation, well, they are useful for different purposes, but still One of the problem with graph is that there is no natural ordering in the vertices and the edges. So these representation cannot be used to perform different operations on the graphs, right? And so traditional statistical methods, machine learning techniques cannot be directly applied to the graphs using these representations. So for example, comparing two graph, one idea might be to use exact matching, but that is not practical because of two reasons. The first reason is that subgraph isomorphism is NP complete. And the second is that the process of acquiring graphs may introduce some sort of noise in the graph. And so at the end, we are comparing two graphs which might have different number of vertices and edges. So to overcome these problems, two widely used approaches are inexact method and decomposition method. And my research focus was decomposition method, so I'm going to discuss them in some more detail here. Decomposition method decomposes the graph into smaller substructure and then uses those substructure to embed the graph in some low-dimensional feature space. Common approaches are use random walks or shortest paths or graph-led cycles, trees, etc. And there are generally two types of decomposition methods. One is called implicit embedding and one is explicit embedding. Graph kernel are perhaps one of the most important approaches for implicit embedding. It's a positive definite kernel on the set of graphs, which measures the similarity between graphs by assuming an implicit embedding of the graphs in some Hilbert space. They can be defined on different types of substructures, and they're also suitable for labeled graphs. For a good graph kernel, there are 4 different criteria that must be met. One is it should be expressive, it should be efficient to compute, it should be positive semi-definite, and it should be applicable to a wide range of graphs. And in the last 2 decades, a number of different graph kernels have been proposed, but most of them suffer from the limitation, like there exists a sort of trade-off between these criteria. Some are expressive, but they are not efficient to compute and so on. One of the most popular graph kernel, which was proposed in, I guess, 2002, is the random walk kernel. It is based on the frequencies of matching random walks, and its computation is very interesting. It is computed using a product graph formalism. So how it works, first, given 2 graphs, a product graph is constructed in such a way that a random walk on a product graph matches a random walk on the 2 input graphs, right? And then the frequencies of walks of different lengths, this graph actually corresponds to the frequencies of matching walks on these 2 graphs. So it uses a variable epsilon, which actually is used to make sure that the graph kernel converges. There are a number of advantages of random walk kernel. It is efficient to compute using product graph. It can be applied to large family of graphs, to labeled and weighted graphs as well. And there are also some limitations. And one of the limitation of a random walk kernel is that it tends to map non-isomorphic graphs to the same point in the feature space due to their co-spectrality. So 2 co-spectral graphs which are not isomorphic, they might be mapped to the same point in the feature space. Another problem of random walk kernel is the problem of torturing. So for example, in this graph, a random walk OCCCCH of length 5 might correspond to a random walk on 6 different vertices of the graph or 4 different vertices of the graph. That reduces the power of the kernel. So to overcome this problem, one idea is to use backtrackless walk kernel. And one way to compute backtrackless walk kernel is to transform the graph into oriented line graph. A oriented line graph is a transformation where every edge of the graph is replaced by two vertices, and it is constructed in such a way that a random walk on the oriented line graph corresponds to a backtrackless walk on the original graph. So the frequencies of random walks on the so a random walk kernel, if we implement it on an oriented line graph, this will correspond to a random to a backtrackless walk kernel on the original graph. But the problem with this is that if we have a dense graph, we'll probably have many edges. So the size of the oriented line graph will be very large. So it might not be practical to compute this kernel on this type of graph. So we developed a method that computes the backtrackless walk kernel directly from the adjacency matrix of the original graph instead of performing any transformations. So this actually is done in pretty much similar way as the random walk kernel is computed. Its worst case running time is same as that of random walk kernel, which is big of v cube. But in practical situation, it runs a little slower than random walk kernel because it requires more operations to be performed. And as I said, there is always a trade-off. So although it improves the accuracy, it has slightly less computation time, slightly higher computational time. And it also is less prone to the problem of failing to distinguish co-spectral graphs, which I'll explain later. Right, we have also developed graph kernels for cyclic graphs. And this was done by using Ihara coefficients. The Ihara zeta function of a graph is an infinite product, which is defined over prime cycles. But its reciprocal can be written in the form of a determinant whose coefficients are related to the frequencies of prime cycles in the graphs. And that justifies their use for characterizing cyclic graphs. But again, their limitation of the Ihara coefficient is that their computational time is very high. It generally requires cubic time in a number of edges in the graph to compute the set of all Ihara coefficients. To find efficient method for computing Ihara coefficient, we have shown that the nth Ihara coefficient can be expressed using nth Bell polynomial. We have then developed a recursive formulation for Bell polynomial. And then using this relation, we have developed the method that can be used to find the nth Ihara coefficient recursively. Initially, we have shown that if the eigenvalues of the oriented line graph, they are known, we can compute all the set of all coefficients in e-square time. Then in another work, we have shown that the lower order Ihara coefficient, we have developed another method for computing the lower order Ihara coefficient in v cube time. Now, the lower order Ihara coefficient contains more important information for characterizing graphs. And that is why they are more important for as compared to higher order coefficients, because they might contain some redundant information. Another advantage of using this identity is that it allows us to find the structure of each Ihara coefficient. So we have shown that C3 is the negative of twice the number of triangles in the graph. And similarly, C4 and C5 are related to the number of squares and pentagons, simple squares and pentagons in the graph. Similarly, the higher order coefficient gives us some more information. So for example, C6 is related to the number of triangles and hexagons in the graph and so on. One of the application, as I said, the Ihara coefficients are very useful in characterizing cyclic graphs. So we have shown how these coefficients can be used to cluster different views of an image. So here we have 4 different images, and each image has 72 different views. So we have 72 times 4 different graphs, and we try to cluster them using Ihara coefficient. This is the result which was obtained by embedding the feature vector in a 3-dimensional space. By the way, it's an explicit embedding. We can also use Ihara coefficient for the label graph, where it will give us implicit embedding, and in that case we can again use the product graph to compute the similarity between the graphs. Right, so as I mentioned, Ihara coefficient backtrackless graphs, they are less prone to the problem of failing to distinguish co-spectral graphs. So these two are non-isomorphic graphs, but they are co-spectral. They are co-spectral with respect to their adjacency matrix. So it means that their adjacency matrix share the same eigenvalues, as well as they are co-spectral with respect to the adjacency matrix of their complement graph. So when we computed the random walks, we can see that R1, the random walk of for graph 1 and graph 2, they are same. But the backtrackless walk, it embeds the graph in a different feature space, because these values starts changing from 5th component and so on. Similarly, Ihara coefficient gives different values for these two graphs and for the other pairs as well. Right. So in the last part of my talk, I'm going to talk about quantum graphs, which was actually the initial topic of my research. I started with quantum graphs, and then I have to move to backtrackless walks, other things, and then I've shown some connections of the backtrackless walk with the quantum graphs and so on. So what is the quantum graph? A quantum graph is a metric graph which is equipped with the differential operator and suitable conditions, boundary conditions. So each edge of a quantum graph is assigned a real length. So edges are real length interval. We assume that the graph is lying in a high dimensional space. So, and we associate a variable to every edge of the graph. So now our graph lies in 2 spaces. One is the node space, and the other is the edge space. So this led us to 2-part Laplacian. One is the vertex-based Laplacian, which is the traditional discrete Laplacian, and the other is the edge-based Laplacian. And now the graph, the functions now may exist on both vertices as well as on the edges of the graph. The edge-based Laplacian of the graph is more complex, and it's also difficult to compute. So the eigenfunctions of the edge-based Laplacian, there are 2 types. One is the vertex supported eigenfunctions, and the other is the edge interior eigenfunctions. So when I was working with the edge-based Laplacian, initially we had no idea about the edge interior eigenfunctions. I started implemented using vertex supported eigenfunctions, and we realized that they are computed from the normalized adjacency matrix, and we realized that they are directly related to the eigenvalues of the normalized Laplacian normalized adjacency matrix, and they're related to the random walks on the graph. When we implemented that, and when we tried to implement different partial differential equations, we found that there are some missing eigenvalues in the function, right, in the system. So then we identified that there are edge interior eigenfunctions which are 0 on the vertices. And those eigenfunctions can be computed from the eigenpairs of the oriented line graph, which means that the eigenfunctions of the edge-based Laplacian, the edge interior eigenfunctions, they are directly related to the backtrackless walks on the graph. We have then developed explicit methods for computing both the vertex supported eigenfunctions as well as the edge interior eigenfunctions of the graph of the edge-based Laplacian. So the vertex supported eigenfunction there comes from the normalized adjacency matrix of the graph, and the edge interior eigenfunctions come from the oriented line graph of the graph. So the advantage once we know the edge-based eigenfunctions, its advantage is that we can define and solve more complex partial differential equations on graphs, which has more close meaning to the partial differential equation in analysis. Because we don't have any discrete space, we have now a continuous space where we can define partial differential equations. So initially we used a heat equation, and we have solved heat equation using the edge-based Laplacian and used its solution for analyzing three-dimensional shapes that are represented by means of a mesh that approximates the bounding surface of the shape. We have used it for correspondence matching, shape retrieval. So for example, in this case, this is a 3D shape, a Curie shape, and these are the 5 best matches in a data set of, I guess, 200 different shapes. Similarly, this Curie shapes return that, this Curie shape return these shapes. We have also used it for correspondence matching, right? And we have used it for shape clustering as well. Further, we have also developed method recently to estimate the entropy of a graph using the solution of an edge-based heat equation. In another work, we have solved the wave equation on a graph and use its solution to characterize graph. Now the wave equation, which if we implement it using a discrete Laplacian, it has certain limitations. For example, it does not have finite speed of propagation. But the wave equation, which is solved using the edge-based Laplacian, it is more close to the wave equation which is defined in analysis. So let me show you this simulation. So here we have a graph with the 5 vertices. We assume that there is a Gaussian wave packet which is fully contained on a single edge of the graph. Then we, with the time, we look at its evolution or the graph using the amplitude of different waves on different edges of the graph. We have constructed a signature, and then we have used that signature to compare different graphs. There might be other advantages of using this type of partial differential equations. It still suffers from the problem of computation time, because I said this computation of edge-based Laplacian requires us to first transform the graph into oriented line graph, and then perform an decomposition of the oriented line graph, which is a very expensive operation. So it would be interesting if we can get these eigenfunctions without transforming graph directly from the original graph, as we did for Ihara coefficients and other things. Right? So my current focus of research at the Institute of Cancer Genomic Sciences includes developing these novel graph-based methods and explore their applications in more biomedical and clinical settings. So, for example, very recently, they have shown how graph kernels, we have developed different graph kernels, and we have shown how graph kernels, the efficiency can be improved for biomedical data sets. We have used Bayesian networks to infer gene regulatory networks from gene expression data. We have implemented different diffusion processes on graphs, which I've already explained in my talk. And finally, a problem which is of both theoretical and practical importance, link prediction in complex networks. So we have shown that how this problem can be used for predicting missing links in a network. These are some of the work, as I said, like most of the work is from the edge-based operators graph characterization. It's my thesis, which can be found online, and some other related references. So thank you very much. Any questions, please?
Okay, thank you, Furqan, for this interesting talk. Is there any question from audience?
Hi, yeah, I have a question. Hi, yeah, very interesting talk. And I guess actually my first question here is, I'm just curious, like in practice, usually the network structure or the network structure is available, or you need to kind of estimate them by yourself?
So what you mean by network structure? Sorry.
Like it's, you know, kind of how they are connected to each other.
Yeah. So yeah, there are like there are different scenarios. Sometimes we already have the network structure, right? And sometimes we don't know the network structure. We only have sort of data given in the form of a table or something like that, right? And in that case, we use something like maybe mutual information or other statistical measures to find the relationship between the nodes of the graph, right? So in that way, we connect the nodes. So then we look at like different properties of the network. For example, is it a scale-free network, or what threshold value can be used to remove the edges from the network and to get a structure which can be used for further analysis. Right.
Yeah, thank you. And actually, just another quick question. So just out of curiosity, so it's actually related to the kind of the PDE you just talked about. So I sort of understand kind of how you define the Laplacian on the graph. I'm just curious, like, is there any kind of connection between, you know, the graph and high order derivatives, like a third order derivative, fourth order derivative?
Well, I'm not sure because I'm sorry.
Yeah, I'm just curious because you define the Laplacian in a very special way, right? So I'm just curious, like, is there some relation between that and, you know, higher order?
We have not explored any higher order, so I'm not sure really. Yeah.
No problem. Thank you.
If you can define first order derivative on graph, right, then the second order, third order is basically apply some linear transformation, right? Let's say it's the first order derivative, because this derivative is linear, right? Linear operator. Once you can define this metric L, let's say L is your differential operator. The second order will be L transpose L, right? Something like that. Okay. And the third order will L transpose L, right? So something like that. So I think if we can define this derivative on graph, first order derivative on graph, then it should be possible to do third order or fourth order. Yeah.
Okay. Yeah.
That might be possible for discrete Laplacian, but I'm not sure about the continuous one.
Yeah, that's a good point.
Yeah, I mean, discrete L square, L cube, you can define them, but for continuous, yeah, I'm not sure. Sorry.
Yeah, thank you. Yeah.
So, Furqan, I have a few questions. When you solve this heat equation, how do you select T, the time step?
Well, it depends on the problem that we use solving, right? So in practice, the maximum value of P is determined from the second smallest eigenvalue and the minimum from the largest eigenvalue. And it has been shown that if we select the value of P between these two ranges, that gives us most of the information about the graph. Right? So they're determined from the eigenvalues of the Laplacian.
Okay, yeah, I think that makes sense. Also, when you solve this heat equation, you need to initialize something, right?
Yeah, yeah.
How do you do initialization?
Yeah, so I've actually solved a couple of problems with that. So in one case, I assume that all the heat is contained on one edge of the graph, right? So, and that is normally distributed, right? So mid of the edge contains most of the heat, and then it allows the flow of the heat or the graph. In the other case, we assume that there is a unit heat on every point on the graph, and then we allow the heat to flow. So it is that we can show that it's directly related to curvature of the shape. So if a shape is like more bent, the heat will flow fast and slow if it is more flat.
Okay, okay, that's clear. And my last question would be: I know heat equation has closed form solution, right? So can you derive closed form solution on this graph as well?
Yeah.
Okay, thank you.
Yeah, I've used closed form solution on the analytical solutions, not the numerical solutions. Yeah.